I'm happy to welcome today Professor Laura Lewis from Northeastern University. She's a chemical engineer uh, as well as a mechanical and industrial engineer at Northeastern. She's going to speak to us today about magnetic materials. You know, magnets are just ubiquitous. They're in all sorts of engineering systems. But as these systems evolve, the need for high strength magnets has increased dramatically. And Laura has been investigating an interesting material, a material that is very difficult to find and probably just about impossible, I think, on the Earth as a natural material, but one that can be synthesized in Laura's laboratory. So this is the evolution of a material that is of great consequence, I believe, going forward in terms of all sorts of applications in our technological world. And Laura, I'm just delighted to have you with us today. I am going to turn the floor over to you so you can screen share whenever you like, and welcome to the Wilson Forum.
Great. Thank you very much, everyone, and thank you for the invitation, the introductions, and I hope that I will be able to advance your knowledge in certain areas, a very wide background of people. Let's see, I'm very open to questions as well. So. All right, I am very hopeful that everyone can see my screen.
Yep.
Great, okay. And I'm going to, see if I can, there we go, pointer option. I'm going to use a little electronic laser pointer. Mm-hmm. The topic, which Ron and I agreed on, the title is Synthetic Tetrataenite, Extraterrestrial Origins, Terrestrial Consequences. There we go. So this is a story about magnets. And I'm going to go into a little bit of detail about what the big deal is about magnets. And Ron very nicely already gave me an introduction there about that. So first we're going to do what the big picture. Why should anybody care about magnets? So broadly speaking, magnets allow interconversion of mechanical and electrical energy, allowing energy transmission, generation, and a quickly changing world needs new and better magnetic materials. We'll talk a little bit about that, why that is the case. Here is an example of some 21st century aspirations that require strong magnets. We've been hearing about robots everywhere. However, robots will not work unless there are magnetic magnets in them to transfer electrical and mechanical energy. Drones, same thing. Electric mobility, electric cars. We've also, not so much anymore, heard about this transport idea called Hyperloop, and I won't go into that, but so I have a question mark. I think it's questionable if it's going to work at all. But we've been talking about magnets in that. And then certainly overall in advanced manufacturing. These are all topics of interest to the United States, and they all require magnets. So this is a bit of the basics of what I'm going to call permanent magnets. And I'm going to be giving a bit of the basics so that later some of the information that I will provide has more of a, maybe is a little bit more accessible. So we're not going to talk about refrigerator magnets, although these are indeed permanent magnets. They will have a magnetic flux in the absence of an applied field. We're going to talk about something that's much more compelling. So a bit of background. These permanent, we also call them hard magnets, they store energy. So if I were to send you to the laboratory, I would give you a magnet and I would say, okay, I want you to apply a magnetic field and measure the magnetization. Here's what a permanent magnet would show you. You would start out at zero magnetization, at zero field, apply your field, and one would advance the magnetization to a certain state. Now, if you then took the magnetic field back off, one does not go back down to its original state. There is a metastable state that the magnetic field in the magnetization follows, and the energy that is enclosed by this hysteresis loop. This is the indication of the stored energy. Additionally, it's a little bit of a different topic. We're going to revisit this, but I just want to give a definition now. Magnetic materials, due to energy considerations, will spontaneously organize into domains of uniform magnetic polarity. So I'm going to talk about this. We've got some Maxwell equations for the electrical engineers. If I were to provide a magnetic material, and you can follow these lines, these are del dot B means the magnetic flux lines never have a beginning nor an end. This is an extremely, extremely high energy state. The material will spontaneously start to split into domains, and now you can sort of schematically see that this energy is much lower. This is a favorable state, and the material is clearly smarter than any engineer, and it will create its own magnetic domain state. So here are some examples of magnetic domains. These were captured actually by my laboratory, undergraduate students as well as graduate students. And let's see what you're looking at. These were captured using a technique called magnetic force microscopy. But you are seeing the magnetic domains on the left on silicon steel for motors, and on the right a particular exotic compound. These are false colored to emphasize the magnetic domains. But if you look on the left-hand side, you might be able to see that the magnetic domains have this elbow that's at 90 degrees. Only materials that have what we call a cubic structure can sustain this. So right here, this is one way to tell your crystal structure from the magnetic domain structure. These were just pretty pictures. The information is not quite relevant right now, but wanted to show you some fun examples of pictures of magnetic domains. So now we're going to advance to the case for new types of hard or permanent magnets. And this is work that has been funded throughout the years by a number of different organizations, most notably Rogers Corporation, Department of Energy, and ARPA-E, Department of Energy, and NSF. So what you're seeing here is how much magnet is needed to exert a particular force in a device. And if we go down to the most advanced magnet in 1940, this was Alnico, and you can see that a volume, I'm not exactly sure what the force is, but these are all equivalent. You can see that you need quite a lot of magnet to get a particular force out. And then we can advance all the way up to the 1980s, 1990s, to these different types of magnets. One, the N, stands for neodymium magnet, and the other one is samarium cobalt. We'll talk a bit about that, but you can see that these are much, much lower volumes of magnet that's necessary. So that means that we can decrease the size and increase the efficiency of whatever devices utilize these magnets. These up here are called the rare earth supermagnets. And here is the periodic table. I know that you all, like me, dream about this at night. And the rare earth elements are these that are in the lower portion right here. They are, among other properties, very, very difficult to separate from their natural ore because the electronic structure on the outer electronic shell looks the same. When you add electrons, you add and you go from lanthanum, cerium, praseodymium, as your atomic number increases, you're adding electrons to the inner shell of the atom, and therefore the outer shell looks the same, and it's very challenging to chemically separate. So although rare earth magnets are truly the best that we have, the rare earth elements have a lower abundance and an uneven geologic distribution throughout the world. And if you look at this image right here, we have abundance of atoms of elements on this axis and the atomic number on this axis. And this graph has been divided up into an OK region above this green line and a rare or used sparingly region below the red line. And you can see that many of the rare earth elements straddle this line right here. You can also see that, especially for semiconductors and such, some of these are of interest, but they're very, very the most rarest elements that we have. So these are quite abundant. These are not. And right now, this number changes. I will maybe say 80% of the rare earth elements are processed in China, and these create very challenging strategic supply issues. And indeed, this has been throughout the media. I'm sure everybody has seen this. These are older headlines from Forbes, Reuters, New York Times. However, this issue has not done anything except become more, actually a little bit hotter. And indeed, this was in 2021, but it's still a very important issue about America's supply chains for materials, including rare earth elements. And right now, the United States government is providing lots and lots and lots of money to try to create domestic supply chains of rare earths. And that is, I could talk about that later, but you can throw money at an issue, but money doesn't always equal solutions. Very recently, this is from March 2023, Tesla is going back to electric EV motors with no rare earth elements. They're flipping around. We know that the motors that contain magnets that have rare earths are more reliable, but the supply chain is less reliable. So they're trying to balance what they're going to be doing. And in the magnetism community, we're still trying to figure out what this means because we are not sure it's possible. So with the interest of reducing pressure on strategic materials, I'm going to introduce to you a cosmic mineral called tetrataenite, and I will allow you all to decide whether or not this is a potential game changer. So first things first, what is tetrataenite? Why is it interesting? And many of you maybe have not ever heard of it before, so I'm going to answer these three questions. Tetrataenite is a ferromagnetic mineral, and by its definition, it has a tetragonal structure that we call chemically ordered. So let me first go down here. This is regular old alloy iron nickel. You can see it's a cubic structure, and there is no particular arrangement of where the atoms sit relative to one another. We call that chemically disordered or atomically disordered. Now, tetrataenite, and in this case, the magnetic directions go along all three axes, and that's not useful for technology. You need a magnetic direction to go one direction or the other to provide a binary or an on-off state. This is tetrataenite. You can see that we have a slightly tetragonal structure. It's no longer cubic. We have extended this axis right here. And now this has this compelling chemical order or atomic order where if orange or nickel atoms, they align in a plane, then we have iron atoms and then nickel atoms, and they will continue to build on up to create something we call a superlattice. So those of us in material science understand a superlattice is a type of hierarchical order. And when these atoms align themselves, a very strong magnetocrystalline anisotropy, a strong moment, gets locked in, and it is now a useful one because it is uniaxial. It only goes up and down, and now this could be utilized for engineering purposes. Based on some of our work that we did on natural samples that were meteorites, if we are able to engineer tetrataenite perfectly, it can be 66% of the strength of the best rare earth magnets that are out there, but it does not contain any rare earths, no critical elements. And I will say that even at 66% of the strength of the best rare earth magnets, I still could not pull that off of my filing cabinet. So where do people start hearing about tetrataenite? So strangely enough, the first report of it was out of France. Louis Néal was a Nobel laureate. And for some unbeknown reason, they took a single crystal of iron nickel and they put it in a high flux neutron beam. I don't know why they did that, But when they did it, they found that they found some of this evidence of this chemical order that I just showed you right there. And this paper must be very controversial. I read it in French, which is not my great language, and in English. And at the very end, the authors disagree. They agreed to disagree. At the end, they say Louis Néal believes this, and the rest of us believe that. So I don't know what was going on, and I do hear some of my colleagues in the magnetism field went to meetings with Louis Néal, and apparently he was a bit of a challenging character. Now, nothing happened until at least 10 to 20 years, where now meteorite scientists, meteoricists, started to find this order in meteorites, and these were formed over billions of years because they need to form this structure. They need a cooling rate of 0.1 Kelvin per million years to 100 Kelvin per million years. This is what's in the literature. And after that, in the 2010s, people started to think, I wonder if we can develop this for permanent magnets. And primarily, the players in that field were my group, and I was working on bulk materials. I call them bulk because you can hold them in your hand, and they're available for engineering purposes. The rest of the groups worked on it by creating ultra-thin films by monatomic layer deposition. So they can make maybe 10 atomic layers of this stuff, and that's it. And I said, well, that's not so useful because we're never going to be able to put this material in a wind turbine if we're going to use atomic layers of it. So why is tetrataenite not used today? So I'm going to show you right now, for those of you that are metallurgists or have worked in metallurgy, these are sort of recipes to get different phases. And this is your standard iron-nickel phase diagram. If you're going to make steel, this is the basis of steel. This is on industrial timescales. There's no tetrataenite here. This is what my colleague, who since passed away, Joe Goldstein, called the modern iron-nickel phase diagram. This was derived from meteorites, and you can see at astronomical timescales, they do see this L10, which is the crystal structure designation of that chemically ordered phase. I don't quite think this phase diagram is correct. This was from 1996, but nonetheless, this is why nobody ever sees this, because these materials are not found on Earth. To form tetrataenite in large amounts, you need up to 1 billion years. So if we're going to do this, we're going to have to really accelerate that formation. So if we're going to accelerate the formation, can we actually do it? And then once we do it, can we even recognize it? The superlattice, those layers, are very, very, very challenging to discern because iron and nickel are so similar electronically. That signature is very challenging. So first we're going to try to look at efforts of can tetrataenite formation be accelerated. So this is a strategy. We're going to try to favor thermodynamics to try to get that ordering to happen. So this is a image, which those of you who might have remembered thermodynamics, we have here equilibrium, where we have one phase, which might be the regular disordered iron nickel, and another phase, which might be the ordered iron nickel. We talk about this is the Gibbs free energy, and we say that the Gibbs free energy is equal in these cases. And that's what we call equilibrium. And this is a framework that we can use to understand how to form things. So I think everybody can see that what we need to do is tip the scales one way or the other. And that's what we're trying to do. If we can tip the scales one way or the other, then we can favor the formation of the material that we want. And the way we can do that is to start to add different energies onto our phase transformation. In nature, really temperature is the only driving force or parameter for phase transformation. But if we can add in some magnetism, this is electronic interactions, we can strain it, we can put pressure on it, maybe we can tip things over. So with this philosophy, we decided we're going to try to augment the driving force to accelerate phase transformation. How did we do that? We went ahead and built what we call the multi-driver furnace, and it is a very unimpressive piece of equipment. So it is just a basic furnace, and those of you who have been in a lab, you would not be impressed by this. But what is impressive is that when we put our sample here, we have some permanent magnets that create a closed flux path so we can anneal in both magnetic field and strain. And we were, after a number of years, just recently awarded a patent on this. This was exciting. And it just goes to show, and I like to show students, that things don't have to look fancy to be really effective. So this was, can we accelerate tetrataenite formation? But now how are we going to recognize that we did it? It's really challenging, and I won't go into too many of the details, but here are some of our ways that we did it. So the best way is we can look at those magnetic domains. And if you remember the pictures that I showed earlier, just to show you magnetic domains, what you're seeing here is the first pictures of tetrataenite that was taken from a meteorite. It says this is from 1980, Clark and Scott, a new mineral in meteorites. And let's break down what you're seeing. So one is seeing three different colors of sets of colors of magnetic domains. You can see light green and dark green. You can see brown and yellow, and you can see light orange and dark orange. You do not see any 90-degree domain walls. So what you're actually seeing are the three variants of tetrataenite that grew naturally in this material. Down here, this thing right here is not magnetic. This is probably some kind of iron sulfide. And when these are all, and also they're, you have to have kind of magnetic domain eyes, and I'm not, able right now to show you that. But if you were a magnetician and you looked at that, and then you looked at this picture here, you would say that these are very similar. And this picture here is an image of the magnetic domains in a neodymium iron boron supermagnet. So this is exciting. This shows that, yes, this is one way to look at the chemical order. So we're going to now go into our efforts on synthesizing tetrataenite on Earth. So here's in about 2017, we had some samples, and these are bulk samples. We have bulk pieces of iron nickel, and we put them in our multi-driver furnace. And right away, you can see there's a very large difference between the conventional anneal, meaning we just cook them, and the multi-driver anneal, meaning that we put both iron and, put both magnetic field and strain on this material. And I will draw your attention to something that I didn't see till years later. I thought it was just an artifact of our technique. I hope you all can see underneath, it looks like we have some stripes. It looks like we have very fine maze pattern, but overlaying white stripes, brown stripes, white stripes. And these actually are true. These are actually real. So we knew that there was a very clear difference in magnetic domain scale and morphology, but we had no idea what this meant. Clearly, we needed something, a technique that was better. And what we did was we found my colleague, who is the best at magnetic domain imaging in the world, and he is at IFW Dresden. He is the world's expert on magnetic domains, and I went to Dresden for a while under the auspices of a German Fulbright travel fund. And after lots and lots and lots of polishing, we noted this was our particular treated multi-driver annealed sample. So if you look at these, you can sort of see that there's 4 different regions. We'll go over these. First, black contrast and white contrast means that we have in-plane magnetization, and gray means out-of-plane magnetization. Gray means you have something cubic. So zones 2 and 4, not very interesting. Zone 1, immediately my colleague said, oh yeah, you've got a uniaxial material here. You have something unexpected. And these are little surface magnetic domains. I won't go into that. And then this one here, if you look at how this hysteresis loop looks kind of like a combination of this one and that one, this is probably a mixture. So we were very happy. And this is, I think, the most compelling image, is if you look at the left-hand side with our magnetic domains, and you look at the right-hand side, this is just the topography. You can see there is an exact one-to-one correspondence between this special black and white and this hard, very difficult to polish sample. I was very fortunate that Stefan, their technician, all he does is polish. He polished the sample for 6 hours, a lot more than the 40 minutes my students did. And therefore, this is a very hard to polish region. We know that this chemical order makes things very hard. And this is actually, if in meteorites, how meteoricists identify tetrataenite, because it's very resistant to polishing. So that was kind of interesting. So we were approaching tetrataenite. We were really happy, but really we have no evidence of that atomic order. So we can't publish things that we have no evidence of. We do know that there's something in here. We certainly have made something, we've changed its symmetry, but we can't see anything about the order. So now we have to turn to other probes to seek atomic order in iron nickel. And these are the only ways that we can do it. We have to do special neutron diffraction, Mossbauer spectroscopy, or transmission electron microscopy. And so I know for electrical engineers, you might not go into this, material scientists do, but we're just going to talk about a little bit about these. But these are the only ways you can tell. And you have to, obviously, have a neutron research reactor to do the first one. You have to have a Mossbauer spectroscopy setup to do the second. And electron microscopy is a little more easy to access, but none of these are easy to access. So what we're going to do, I'm going to show you here, is what X-rays and neutrons see when they probe a material. So if we look at iron and nickel, you can see they're almost exactly the same. So X-rays cannot tell very easily whether or not we have iron and nickel like this. Neutrons, same thing. Iron and nickel, we cannot tell. They're very similar in size. I can't tell the order, but nature gave us something very unusual. Nature gave us nickel 62. It is an isotope of nickel that has what we call a negative scattering cross-section. I don't know quite what that means, but it means now that these guys are so different that you will be able to see the superlattice very, very, very easily. So we were able, with the help of Northeastern, to purchase nickel 62. You might be surprised, or maybe not, that a gram of nickel 62 costs $10,000. So these are very precious samples. And we went ahead and made some samples and took them to Rutherford Appleton Laboratory. One of my good friends is head of neutron scattering. And this is outside of Oxford in the UK. So we're still trying to see if we've got this atomic order. We know we've done something, we just don't know what we've done. And I know this is a little technical, but I'm going to show you some differences in what neutrons see. If we have something that scatters quite nicely, we can also have iron and palladium put together. If we look at them with X-rays, these are the same crystal structure, different elements. The stars are the signatures of that order. So we're lucky with iron palladium. Yes, we see lots of order when it's ordered, but iron nickel, even if it's perfectly ordered, we just can't see these peaks. Now, if we take this to the neutron facility, what you're seeing here now is what we would expect. These are derived from modeling. If we did natural iron and nickel, still we don't see anything where these peaks are. However, with nickel 62, all we see are those peaks. We don't even see the other ones. So this was what we tried to do, and I'll say tried in a minute. This was data taken from 2019, right before the pandemic and right before the this particular neutron beam line was set to be shut down. So we couldn't really get a lot of data. And at first look, what you're seeing is, this is our nickel 62 reference. The data are red and blue. And I was hoping, oh, I would see peaks where these green ones are. And unfortunately, I don't. And I was really disappointed, but I don't give up easily. And I thought, well, wait a minute. I don't think there's something there, but maybe if I go down and I really zoom in, I see these oscillations. I'm like, what is that? So when I match up the oscillations with the anticipated data, it looks like there might be something there. It looks like we have a very, very low level of atomic order. My colleagues at the Rutherford Appleton Laboratory were not comfortable with these data. They thought this might be due to something else. They weren't comfortable in publishing it, so we have data. This has not been published. And we were not able to redo these experiments. Recently, I just received one more day of time, but the beam line has gone down again, so we are still trying. So this is not an experiment to be pursued in a quick manner. So, still seeking atomic order. So I have a colleague in Dublin, it's a very international project, who's an expert in Mossbauer spectroscopy. What is Mossbauer spectroscopy? You can think about it as a fingerprint, a nuclear fingerprint of different atomic structures. It's a very local probe. You can only tell what's going on around the nucleus of the atom, but it is widely used to look at meteorites. And so I'm not going to go into too much detail about this. I'm happy to answer questions later, but I don't think it would be very useful right now to go into detail. But you get this absorption fingerprint that's very easy to analyze, and it corresponds to different crystal structures. So I gave these materials, instead of coming back to the US, they went from England to Ireland. And then we started looking at them, right around the pandemic. And the data here was not the data, but the acquisition, because my colleague and his family got COVID, and it was a lot. So my colleague, Plamen Stamanov, is a physicist at Trinity College in Dublin. He called me up. He said, oh, Laura, you've got tetrataenite. I'm like, what? This was in 2021. And he sent me these data. And I said, that doesn't look like anything. I do not see any difference. But through what is standard in this procedure is now, once you process the data, you can see a very clear difference, red versus the blue, between the two samples, same samples, just processed differently. And in our conventionally annealed samples that we sent, there was no tetrataenite. Everything was this cubic crystal structure disordered. We looked at a piece of our meteorite for calibration, and that was 80% tetrataenite and 20% of this disordered phase. And that's to be expected. We already knew it was a meteorite. We knew it had it in there. Now, the sample that we measured had 21% tetrataenite, and the rest was cubic. And we thought, oh my God, we've actually done it. So that was 2021. We were finally able to just now submit a paper to Advanced Science. And just for summary, everything that was subjected to multi-driver annealing, this is field strain annealed, they all have on the order of 20% tetrataenite, 80% non-transformed. This is now 2023. That was 2021. It takes quite a while. So what's next? Are we going to be making magnets that will now take off the supply pressure? So this is to give this some context, this is a map of strongest magnets as a function of time versus their strength. And we have this in units that North America uses and units that Europe uses. Kilojoule per meter cubed versus megagauss Ørsted, but they're equivalent. The strongest magnets were steel magnets in the 1920s, developed by the Japanese. As we increase in time, rare earth magnets started to come up around 1980. They were dominant, 2000s. And if we are able to create tetrataenite, we believe it would be right around here in terms of strength. So we know, though, that we can get a higher energy meaning a higher value here, but it is much more complex than we anticipated because we've been studying meteorites now and finding out that what we determine from our meteorite is actually much more complex. It's just like anything where you look at it with a finer probe, you find more stuff. Might be as much as 10% higher. So, where are we now? And this is one of the reasons I requested that Ron please not widely distribute this. Industry wants magnets now. You look at all the geopolitical issues that are going on, all the money that the Biden-Harris administration is putting out towards creating domestic supply chains of magnets, and especially those without critical elements. They want them now. And I equate this is my way of explaining things. I equate this that they want the Taj Mahal. They want it right now. So in order to actually get a magnet, you have to optimize the structure, not just the crystal structure. It's not just enough to get those atoms aligned. We have to actually arrange the crystallites. So we are quite far away. And I say that is the equivalent of building a wall. So we're not going to give you the Taj Mahal. It'd be great if we could give you like a wall of the Taj Mahal. But right now, what we're trying to do is make that crystal structure. And so I say equivalently, I don't even have bricks for you guys. I have some powder. So I am very cautious of not raising expectations, as I believe is the responsibility of a scientist. However, other people are perhaps not as, don't have the same thoughts as I do, and there are many reports out there that people have made things that I don't think are true. But I believe, yes, indeed, we have made tetrataenite, and I think we are still very early in the technological TRL, technological readiness level. We're not going to be making these things anytime this soon. However, it appears we have accelerated nature by a factor of 1 billion. Can that be true? And you can imagine all the different experiments we could do to confirm that. So right now, we have a few projects on this, and one is through the Department of Energy. It's a collaborative project between Northeastern University, University of Delaware, and the University of Warwick in the UK, because they are the best in terms of modeling to tell us what we can do. So with that, I'm going to say thank you, and I can stop sharing. And I do have, if anybody wants to see it, I'll stop sharing eventually. I have a video of what these magnets can do, rare earth magnets, if anybody wants to see it. So it's kind of a fun video of magnets smashing cherry tomatoes and such.
Thank you, Laura. This is a wonderful summary of a marvelous set of research initiatives to get to this stage. But, you know, I said at the outset that I think magnets are ubiquitous in our technology and social fabric. But I think people don't in general realize that that is the case. Just for reference, if you could produce these magnets on a scale needed for industrial application, what sort of applications would they be useful for? I mean, there's such a huge dependence on the supply chain and critical materials like the rare earths, that if we could avoid that, this could truly be a game changer in terms of our technology. It really could. That's not an overstatement. But just for reference, for our community here, where would these be applied if you could get them at a stage where they were manufactured in shapes and sizes as required?
Yes, they would be in intermediate applications such as wind turbines, probably energy harvesting from waves and tidal sources, electric cars, electric vehicles, which is huge. There's just not enough of them. There's not enough rare earth magnets for that purpose right now.
Yeah.
The military has a very strong need for advanced strong magnets for all sorts of purposes that are related to weapons. Those would still probably be rare earth magnets, and they would be samarium cobalt because they have a very good thermal performance. There's magnets in your airplanes. There's just magnets everywhere. And so the criteria of whether or not this would be accepted into technology is very, very stringent. They have to run a lot of tests. But it doesn't contain rare earths. And rare earths have some other issues going on with them.
Yeah.
They are very, very susceptible to corrosion.
Yep.
They rust very quickly. So biomedical applications may use these magnets as well.
Yeah, yeah. You know, the interesting thing to me, the iron neodymium iron boron magnets, are they produced by rapid solidification, aren't they?
There are two different pathways within the intellectual property literature. One was rapid solidification that was developed by General Motors and in small part Naval Research Lab, and the other one was developed, that's a powder metallurgy type, and that was developed by Sumitomo, which turned into Hitachi. So They kind of agreed to disagree. They kind of agreed on territorial ranges, and the rapidly solidified ones are not in as large, I think, of circulation right now. But yes, It can be made with both.
But whether they're produced by rapid solidification or by powders, they are non-equilibrium, are they not?
I believe so. Yeah.
I think that is the case, because the reason I asked is I was thinking of a good friend of mine, another good friend of mine at Northeastern a long time ago, Bill Geeson. Bill and I did some work together on rapid solidification many years ago. And this was one of the things we looked at, although we didn't have nearly this ultimate success that we were hoping for. It was an interesting exercise.
Yes.
Yeah.
And the rapid solidification, the crystallites are nanometer scale, whereas the sintered route, they are tens of microns. So they're much larger.
Any questions from our crew? Go ahead, Wayne.
I have a simple question. First of all, thank you for a very clear presentation to non-experts in this field. When you say, I've heard it said many times, as you did, that these materials are processed in China. What exactly do you mean? Does that mean that they're extracted from the ore? And where are the main source? Where are the metals mined?
Yes, I can tell you about that. So the deposits of rare earth ore, and the deposits are in oxide form because, that's what's stable. The deposits are in Australia, in Inner Mongolia and China. There's some in Vietnam. There's some in Russia. And there is some in North America, sort of at the California-Nevada border. What's really important, though, is not so much the rare earths. We have enough of some of them. There's some that we just don't have enough of. And so your mine may not contain the ones you want. So the ores are everywhere, but they are very challenging to process and pull out, to get the metals out. It requires a lot of nasty chemistry, and China remains very willing to process that, and the US not so much because of the environmental considerations. So that is one of the reasons that the processing went to China. And right now there still is no US capability to take the ore to a metal. The metal, even if we dig it up, it has to be shipped to China to reduce it to a metal, to your rare earth metals.
Thanks.
I'm just curious, how was it discovered that meteorites contain these materials? Obviously people would look at their structure, but how did they determine that extraterrestrial body contained a magnetic material of great consequence? That must have been a pretty illuminating evaluation.
I don't think they knew it was of consequence at the time. It was just a new mineral that they found. There are a number of different classes of meteorites, and I'm not a meteorite scientist.
Yeah.
But one of them is iron nickel meteorites, and they're mostly interested in tying them to the origins of our solar system and trying to understand the rate of formation. And so they were looking at diffusion, and they just found iron nickel in a different form that I think was compelling.
Mm-hmm.
Right now, though, it's set to go off in October 2023. NASA has the Psyche mission, which is going to go to a very large iron nickel asteroid, I guess, that's out there, to understand its magnetic character and to see if that was the core of a protoplanet and tie that to the origins of our solar system. But now I'm rapidly outside of my area of expertise. But
the thing that intrigued me about that led to my question was that I've been reading about some folks who have interest in mining asteroids.
oh gosh, I hate that. I'm sorry. Whenever they say that, it makes me insane. Yeah, I know, and I have to be careful to clarify that we did experiments on meteorites because we have their material. But
you're not too optimistic about that.
Oh my God, no! I really hope that we can do recycling and such on Earth. We don't need to do that. There is increasing, maybe not increasingly. Maybe I just never paid attention to it. But there seems to be a sort of a philosophy of, if we can, we should. And I think if you can, you don't necessarily always should.
Something Elon.
That's it. Let's go to the hands that are up. Michael? Oh, I'm sorry. Yeah, go ahead, Michael.
You had mentioned earlier that you felt scientists have to provide assurances. So with that in the background, I would ask, is the material that you've already been able to produce at 17 to 20%, is that a feedstock for a viable product as it is now? Just notwithstanding the fact that you see some improvements that you can make through the crystallization process.
Yes, it's definitely. I think it's definitely a feedstock. I'm sorry if I'm not answering your question appropriately. What we do know is that the arrangement, we see this phase, but the arrangement of the atoms, we do not have perfect order. We need those atoms, which is a thermodynamic process. They will do that. We give them enough time. We need them to arrange themselves more tightly. And because we do not see the magnetic signature that comes from that nice chemical order. So we know that they're there, but it's not perfect order. So we have to get it perfectly ordered.
Okay.
But I don't think I told you, we only treated those samples for 6 weeks. Thermally treated them instead of 1 billion years. So that's, a bit of a difference.
The reason I ask the question is that sometimes people envision the Rolls Royce that they want to create when they actually have the means to create a Dodge to help fund the Rolls Royce. And it seems like there's only one way that you can go, so that doesn't apply to you. But had you had a viable product as it is right now, I would say maybe you can raise the funds to produce the perfect Mars specimens through the exploitation which I already have. But that doesn't seem to be the case, so thank you for your answer.
Okay, Eddie?
Yes, I've actually got a couple of questions, but I wanted to point out that in Quebec, they were planning on opening up a rare earth mine. And the issues around that seem to be that the province doesn't even have the amount of energy required to be able to do the production of that. At least there was a report and a complaint from the mining company that was looking at it. So there are places where you can get rare earths, but the cost of doing it and the ability to do it seem to be, questionable. And I know myself, I worked a little bit on the idea of opening up a rare earth mine in Arizona many, many years ago. And what I saw was that it was going to be a very difficult and expensive process. So, there are possibilities. My other question, though, is related to kind of clone or equivalent molecular or atomic structures. So what you've shown essentially is that one kind of iron-nickel combination can achieve a higher magnetic field. But can you? But are there equivalent material or equivalent structures that could give you something similar or close to what you're achieving?
Yes, there are. Yes, there's a whole class of materials that are nice ferromagnets that are strong, that have that structure. Unfortunately, they all need palladium or platinum. So they are of interest, and I think they might be actually inside some magnetic recording media. They are, but not. There's not enough of them, of the elements, to create what we would like.
Is it possible you could do a combination between those, and so you at least reduce the amount of palladium required?
When we're talking about, I don't know, kilotons that might be necessary, it's not economically viable to think about using platinum group elements for these magnets.
Thank you. Very good thought.
Albert,
Again, money.
I think you must be muted. We can't hear you. Oh, let's see.
You hear me now?
Yeah.
Okay.
Good.
So if that nickel 62 cost so much money, I lost the point. Do you need it to produce what you have?
No, we need it to detect, to unequivocally detect what we have. The nickel 62 was a test sample. And if we could figure out how to get this material, and it was just for testing. Nickel 62 is, I think, 2% of the isotopic abundance of nickel. That's why they had to separate it out. It was expensive, but it was just to really confirm it was there. Later, we don't need it.
All right, sounds good. That makes sense. And
Yep.
I think I like you. The furnace seems pretty simple to produce what you want. But has anyone tried to bombard the material with neutrons like that Frenchman who got the Nobel Prize? First, to see whether it's doable. And secondly, I presume when you showed us this equation, which has all these different Gibbs energy, presumably there is a Gibbs energy for neutron bombardment. Is that correct?
The neutron bombardment part is to the ultimate goal for that was to knock atoms out of their equilibrium positions and then allow the natural thermodynamic process to take over. So we're trying to create, those are called atomic vacancies. We're trying to create holes in the crystal structure. We can do that in other ways, which we did, but nobody else has put a piece of material into a high energy neutron beam to mess up its crystal structure. But we are able to, for example, the samples that we worked on, they were deformed through a process called cold rolling till they were 2% of their original thickness. And then that means that we create a lot of vacancies. We're just trying to give the atoms room to move where they want to go.
And is that what the Frenchman proposed on the results that he obtained?
There was no motivation stated. They just said, we did this. I think in 1955, there was a paper by an Englishman who through some other data said, oh, there must be something strange in iron nickel. And I think that's what motivated Neyal. But it was all a long time ago. So no, there's no motivation provided of why he was going to put this in a neutron beam.
And given the advancement of our knowledge since then, can we comment on whether it makes sense or not?
Certainly not as a production technique, but definitely it just pointed to the fact we need to alter the crystal structure to allow atomic diffusion to take place. And so we can do that in other ways.
That makes sense. Thank you.
Avi? Let's see. Yes, you have to unmute first. There
I've been trying. There we go.
Yeah, there you go.
Two questions. One, you mentioned that the processing takes place in China and not elsewhere because of environmental concerns. Doesn't matter, I think, to the environment, whether it's being processed in China or here or Australia. I'm curious as to what those environmental concerns are, and if we are just accepting degradation of the environment by the Chinese and not want to do it ourselves, or is there some other consideration? There are obviously strategic questions about this, letting China have, in effect, be the gatekeeper with regard to the processing these materials. The second question is, you're talking about permanent magnets, and I just wondered if electromagnets have a role here in terms of providing the magnetic fields that you're looking for.
So to answer your first question, the creation of a mine and a processing production path could take up to 20 years. So part of it is, yes, the US is trying to reestablish those capabilities, but doing it in an environmentally conscious manner. So all the water has to be then scrubbed and recycled. The chemicals, they need quite a lot of chemicals, they need to be recycled. So right now, that's the barriers.
Does China not observe those formalities? They don't worry about scrubbing the water and doing all these other things? Is that the way they do it?
I'm not sufficiently knowledgeable about that, and I'm not sure they would release that information to somebody like me anyways. So I don't really know. I just, it's historically, they have been willing to do what's necessary. And I think now there are articles out there that the population is suffering from ailments and birth defects and such. So the second one with electromagnets, every time we have an electromagnet, we need a wire. We need to get electrons in there. And so that's for magnetism, permanent magnetism, the fact that it's wireless energy transformation is key. So that's why you need permanent magnets for that. Now, once you get that energy, you need wires to take it somewhere through electrons.
Thanks.
Thank you, Albie. I'm curious about, let's say, domestic initiatives to stimulate the production of high-strength supermagnets. Is there anything like the equivalent of the CHIPS bill for magnetic materials being considered, or what's the legislative answer to that question?
Yes, I think actually it might even be part of the Chips and Science Act. The issue is, and I alluded to it earlier, yes, there's quite a lot of money. There are not just Department of Energy, but DOD, and they don't seem to be very coordinated. This is my opinion, not anybody else's. Mm-hmm. But I will be informal and say they're shoveling money at places. Any place that says we can develop this, they're getting quite a lot of money. But it's one thing to get money. It's another to get people who are, to be able to hire people who are skilled in the field. There's nobody who's skilled in the field anymore. When the manufacturing went to China, there used to be domestic manufacturing, and it was a spinoff of General Motors that got sold to China. The expertise got sold to China, so we need to regenerate the workforce, and we're working on that right now. We have some proposals for education purposes. Yeah,
that's an interesting comment, though. We had as one of our speakers earlier this year, we had Dennis White from MIT's Plasma Fusion Center. And fusion is incredibly dependent on finding the right sort of high-strength magnets to contain their plasma.
Oh, gosh, yeah.
And there seems to be the thought that there has been a breakthrough, a game changer, in terms of those magnetic materials. Given your interest in permanent magnets, do you see any potential for the work you're doing to address any of those questions?
I admit I haven't thought about that, but I think I know they must have a very, very, very strong magnetic bottle, and I think that is a some kind of very strong electromagnet. I
Yeah.
don't know exactly what it is, but it's
but
you can't get permanent.
superconducting.
Yeah.
Yeah,
Go
you
ahead,
can't get permanent magnets that strong.
Eddie.
Yeah, they're superconducting. I don't know exactly the morphology of the material, but it's definitely and their big advance was actually to make the magnets in bands,
Yeah.
so that they could easily open and close them, plus keep them core. So it's a little different application, I think, and the field strengths needed are much higher than you could achieve with your material, I think.
What's interesting to me in terms of fusion, though, is that with the I think some of the research on these magnets was done at Berkeley or one of the California universities, but on the strength of that new high field magnets, there are commercial companies that are claiming one claims they're going to be operating by 2030, which is the maybe pie in the sky, but nevertheless we may be seeing a transition in terms of fusion, which is incredibly dependent on magnets. And if that happens, it will open up a lot of interesting dimensions to magnetic materials research, I think.
It could. I will share a statement that is mine.
Okay.
And it was fusion is and always will be the technology of the future.
Yeah.
So I'm not going to hold my breath for that.
Maybe it is optimism, but I think these new magnets that have been developed they are higher strength than anything they've had in the past, and I think there's some reason to be optimistic, but maybe toned down a bit more than
actually. It does raise some interesting questions, though.
Yeah.
Your material, if you super cool it, what happens?
Not very much. It doesn't change much in its strength of magnetization, and it's already very, very mechanically hard. Once it gets that crystal structure order, it conveys a very, very strong mechanical accompaniment. It's not, you can't deform it like you could with an alloy, so it might get a little more brittle, and that's a big problem too with all these strong magnets. They are very brittle, they break, they can't take high frequencies very easily.
And what about its electrical conductivity? Have you
good point. It's better than the rare earth supermagnets. It's not great, but it's better, and you need that for other things.
Right. I'm just wondering if you may get a permanent magnetic contribution, but you could also run a current through it, which would add to its magnetic. So I don't know if you can do a kind of a combination there I'm just throwing the idea out there like crazy.
Well, one activity that I'm really hoping that we can do, I'm on the IEEE Magnetic Society technical committee. We had a meeting yesterday because we know that the motor manufacturers live in one world. Those of us who work on the materials live in another world. We need to meet in the middle somehow, because we will get, as a material scientist, I will get requests for materials that do not exist. They want the strongest material. They want it to be very tough. They want all this stuff. So I'd like the manufacturers of the motors, including Tesla engineers, to say, here's what we want. And then we could say, here's what we can give you. And then maybe there'll be something in the middle. So there's a lot of designs and all sorts of stuff that we can't access because we don't have that background.
Tom?
It's going to take 20 years for other countries to build the supply chain. Then people are going to wait for the Taj Mahal, perhaps, in your corner of the world. And what I'm wondering is, you've shown us your furnace and the various forces applied. are there centers in the world right now looking for different kinds of furnaces and different parameters and really extending themselves to work in this area?
My answer to that, to kind of work backwards from how you asked the question, was, for example, the main competitors are the Japanese, and they will, first of all, never say anything to me, and second, they will actually say we're not doing this, and then I find that they were. So that's an issue. The advantage of this very simple design was we can apply a magnetic field for months if necessary, so it's very energy efficient. There are magnetic furnaces. They require a very complex electromagnetic configuration. There's no permanent magnet furnaces really. So people might say that's not so useful. It does have some limitations because you need to be able to, you can't heat something at too high a temperature because then your magnets no longer work. Whereas an electromagnetic field would not be subjected to that. But we have some other ideas. The idea is that it's passive, it's energy efficient, and you can really cook things for quite a while. And maybe 6 weeks sounds like a lot to some people, but given that we know it takes up to 1 billion years to form in nature, we think that's pretty good. The final thing I wanted to say is when I do get interest from, and I do get more than I want, interest from venture capitalists and such, their first question is, well, when can you have a product? And if you say anything that is, if I were realistic and I said, well, maybe 10 years, they're not so interested. So there's that balance of, there are, if we had, 100 scientists and we were all working in the same direction, yeah, we could probably very much accelerate that pathway. We don't have that situation, so.
But there must be a fair amount of commercial interest in what you're doing at this stage. Is that not the case?
They really do want it tomorrow. So they could be, and part of it is probably my reluctance to overhype something or overemphasize.
Yeah. Yeah,
I definitely could develop that if I wanted to.
Mm-hmm. Avi?
It's a risk of incurring your horror, having heard what you said about asteroids. I wondered if anybody has looked at all as to, are there, for example, these materials on the moon's surface or on the moon, I guess as a little farther out in Mars, whether there are these, I don't know how you would transport them from Mars or the moon to Earth, but just curious as to whether anybody knows whether there's a supply of these rare earth materials there.
The moon, and part of my educational background is in earth and planetary sciences, the moon is mostly made out of an oxide mineral called feldspar. And I don't think it has, they think it's sort of a piece of the crust of the earth that ended up out there. It doesn't have this metal core. The core of the earth is probably iron nickel. That's what gives us our magnetic, our geomagnetic field. I don't know about Mars. Most of the interest right now in the planetary science world, and I am talking with NASA, is to understand the magnetic record that is in these materials and then how that magnetic record can be transitioned, or how information can be pulled out about the early paleomagnetic environment that the solar system was developed in. So I don't think so.
I believe in terms of the moon, they just recently, there was a publication saying that they just confirmed that it does have an iron core. But, that's down in the core.
Well, one thing the Japanese are doing, and I also am not a fan of this, is there are very deep sea minerals that are in clays that contain rare earths, and they're I think it's in Japanese territory, but they are a few miles down, so they're thinking about doing deep sea mining, which would really mess up the ecosystem. They might be as deep as 5 miles to pull up the mud and then process the mud to pull out rare earths.
Yeah, There you go. If it's an iron core on the moon, we could outdo China and a whole part of the moon here.
Mm,
There you
Talk
go.
about environmental impact.
mm.
Yeah.
Actually,
Could
may have
melt it on the way
forgotten.
down.
I may have forgotten what you said, but what is special about meteorites that have that?
What is special about what? I missed the noun.
About the meteorites?
Oh, what's special about them? They are examples of equilibrium situations. We do not have enough time on Earth to look at these minerals. There's things out there. They've had much longer time. So they were just the first evidence, the first materials we could get our hands on that were confirmed to have this structure. And we could do tests. Nobody had done magnetic tests on that phase before we did.
I think in part that's why people are talking about mining asteroids, and
Yes.
because they are centuries in the making, or eons in the making,
Yeah.
and therefore they do contain unusual characteristics. So there is interest. Laura, I want to echo a comment made earlier by one of our members who thanked you for giving a clear and understandable presentation. And I really do. I want to second that motion. This was a brilliant presentation, and you're talking to a group that has a mixed set of interests and experiences. But I think what you presented today was understandable to all of us, and we appreciate that.
Oh, thank you. I'm glad that worked. Thank you.
It did indeed. So, Laura, I want to thank you. We're reaching the end of our
Yes.
hour, but I want to thank you for joining us today. The recording will be on our website in a matter of a few days, I hope. And we will not send it off to the television station to broadcast, but thank you very much again for joining us. I appreciate
Thank you for the invitation, and thank you all for your attention. I appreciate it.
Good.
Thank you.
Thank you. Thank you very much. Take care.
Okay. I will say goodbye now. Thank you.